In all our previous examples, it's worth noting that we always used the natural axes, natural in some sense, of the y-axis or the x-axis to rotate around. It's not necessary to do that, of course. We could rotate around any axis we like, and we're going to try that here and see what the consequences are for our calculations. So if we rotate around let's find the region first, y equals root x, and 2, 3, 4, there we are. Y equals root x, y equals 0, this axis, x equals 4 here, and we know that goes up to 2. We're going to rotate this time about the line y equals negative 3. So you got to be careful here. This is the line y equals negative 3, and that is going to become our axis now. Notice the region is actually far away from that axis. So the shapes we're going to get, if we sketch them out here, there's our center, are going to be hollow tubes, like so. Oops, a little less like that. Like so. In fact, that inner radius is always the same. You could draw that as a dashed line, be like engineers. And we get something like this, and then like that. So what we have is sort of a donut shape, which gets wider as we approach the front face, as we see it from this direction here, but it has a hole cut out in the middle. Visualizing these things is helpful, but it's actually not strictly required. If you can look at this shape here and imagine what it looks like once it's been rotated, you can just imagine what the cross sections look like. And here again, we're going to slice in the direction that gives us the simplest shapes. So we'll slice this way, like so. Supposed to straighten out more than that, that's fine. Let's call that thickness, well, it's a small increment of x, so it'll be delta x thick. And if we do, or make a slice there, let's bring this out, what are we going to see? We're going to see a large but easily defined outer circle and a smaller but also easily defined inner circle, and this whole thing will be delta x thick. And based on our earlier observations, the volume of this slice can be calculated as its thickness times the area of this cross section, and it's just a matter of finding out what that area is, and that area is given by the outer circle's area minus the inner circle's area. So the whole thing minus the gap in the middle. And if we do that, we'll just move one of our pictures over here a little bit to give us some room to calculate. There we go. If we do that, we can find the volume of a slice now. And it would be the area of the ring times the thickness. Volume is a one dimension, thickness times an area. That gives us volumes. And the area of the ring will be pi r outer squared. That's the area of the outer region, the whole thing. And then we're going to subtract the area of the inner ring, inner circle rather, pi times the inner radius squared. All of that times the thickness, and that thickness is simply delta x. Okay. Now our challenge is to go back to our diagram and find these radii. Okay. So the axis is down here. So if you notice, we had big circles here. Why are they big? Well, because there's a gap already from here to here of 3, from here to here. In fact, the inner radius, no matter where we slice, the inner radius is always 3. Why? Well, we're down at y equals negative 3, and the distance from negative 3 to 0 is the positive value 3. That's just a distance. How about the outer radius? Well, that's defined by this curve, but not by this curve alone, but by the distance. Let's formalize this as our inner. It's the distance from the axis out to that curve, which is made up of two pieces. One is our y-coordinate, and the other part, is the gap of 3. So our outer radius is going to be 3 plus our y-coordinate on the curve. It's a y distance, but it also has the 3. That's the entire radius, is the combination of those two pieces. And so we can write that down, but we also note that this curve is given by y equals root x. So if we want the y-coordinate expressed in terms of x, on this boundary up here, we're going to replace the y with root x. So here's how it works out. Instead of 3 plus y, it's 3 plus root x, still squared, minus pi times the inner radius, which is always 3, that's squared, that entire thing, times delta x. Oops. Let's squeeze it in a bit better there. Delta x. That is again the most challenging part, recognizing the shapes we're talking about and then deriving the inner radius, so distance from the axis to the shape, to the area we're looking at. That's always 3 no matter where the slice is. And then the outer radius is defined as the distance 3 plus this y-coordinate, because remember the y-coordinate is always the distance back down to y equals 0. So we have to add the 3 on top of that. Once we have this, we can proceed to our regular integration step, and it'll be straightforward from here. The challenge is developing this. The one last thing, of course, is where do our x slices start? Well, they start at 0, and we slice, slice, slice out to 4. So that's okay. The delta x, or the limits of integration, will be x equals 0 to x equals 4. So let's sketch that out. The total volume will be the integral, as we just said, from x equals 0 to x equals 4 of pi times 3 plus root x, all squared, outer radius squared times pi, minus pi times 3 squared. It was delta x, now it's dx as we take the limit. And we're almost ready to go. We should simplify before we integrate here a little bit. This is just 9, so that's easy. In fact, we should probably expand this to make it easy to integrate. This is not easy to integrate when we've got the square root inside the squared. So we'll have 9 plus 6 root x plus root x squared, so plus x, minus 9 pi. And we can do a few things here actually. We can bring the pi out front. And we do get a nice cancellation. This 9 and that 9 cancel. And we end up with the integral from 0 to 4 of 6 root x plus x dx. Ah, that's a breeze now, isn't it? Just remembering that root x is x to the 1/2. We can write this out as pi 6x to the 3/2 over 3/2 plus x squared over 2 between 4 and 0. And the pi applies to all of that. Then we have pi times 2/3 of 6 times, we'll do the upper limit, 4 to 3/2 plus 4 squared over 2 minus, and oh good, 0 and 0. Good to go. 4 to the 3/2 is 2 cubed is 8, and 12 over 3 is 4. So I'll have 4 times 8 plus 16 over 2 is 8, and that's 32, and that's 40 pi cubic units, which is about 120 units. So notice a fairly large volume compared to what we've seen before. And again, that's what we get with this shape here, this big shape here, because of the large dimensions of the outer circle. Because we off-centered this, we get a much bigger shape when we're done than we would have had if we just kept it as a radius or a center closer to the actual area we're looking at. That's it. The key thing is the integration step is exactly what we've seen before. The challenge is going to be, repeatedly, the intellectual effort to arrive at the volume of one slice. So focus on that part first and foremost as you go through the practice problems.